Good morning, everybody. Thank you for joining our webinar here today on December 3rd. My name is Chris. I am the marketing account for Rothoblast here in North America, and very happy to have you here again with us. We've got a guest presentation today with Dr. Peng from Clemson University, covering the long span composite mass timber cassette floors with the Rothoblast Sharp metal. And before I pass it on over to him, I also just want to remind you we've got our last few webinars here for December coming up, with this one being the first of three. And the next 2 weeks, we've got two more. Next week's also a presentation on the Sharp plate. And then on the last week, we're going to be covering our SmartBook for screws with some focus on the new HBS plate screw. So without further ado, Dr. Peng, the floor is yours.
All right. Thank you, Chris. I appreciate it. Um, so thank you for kind of joining the webinar today. I'm going to talk about my ongoing research on development of a long span composite mass timber cassette floor system using loader blast sharp metal and also consider other connector. So the long span is designed for carbon storage, adaptability, and the reconstruction. What I mean here is at the end of the service life, the plan here is the whole cassette system, the floor system can be take apart and then reused in a different building or disassembled into component. So this project actually is a collaboration between multiple investigator. I myself is from civil engineering department, and we have two other graduate students, Amin and Sovan Roth, go by Roth, PhD student, helping us with this project. And then Professor Brandon Ross, associate professor at the civil engineering department, and Michael Stoner. So we also have collaborator from architecture department, Professor Dustin Albright, and then two collaborator from environmental engineering department, and one professor from forestry and environmental conservation, Professor Pat Layton here. So you might wonder why kind of showing all kind of tiger paw. Just quickly kind of introduce Clemson University. So the location of tiger paw is where Clemson located in Clemson, South Carolina. So if you wonder how to find Clemson, I often get asked where is Clemson. So if you know Atlanta, Georgia, the home of CNN and Coca-Cola, where it's located. And then if you know where is Charlotte, North Carolina. So if you draw a straight line in between, you're going to find Clemson in between these two cities here. So this is Clemson University. So as I mentioned, Tiger Paw, Tiger is our school mascot. And then as a Southern school in US, we kind of love our college football team. And Clemson is a small town located in a small town called Clemson. The population is about 18,000. However, as I mentioned, we kind of love our Clemson football. During game day, home game, our stadium actually holds more than 80,000 population. And then typically you have similar number of people tailgate. That means they are outside of the stadium. They might not kind of join the game. So all of a sudden during football game day weekend, home game weekend, the city become the second largest city in the South Carolina with population up to about 200,000, right? So again, this is some picture of Clemson. You get close to Clemson when you drive along the road, you start to see tiger paw along the road here. That means you are close entering the Clemson uh, town city. So by the way, this is not what I'm here to talk about. Uh, so here quickly, just give you some outline what I'm going to discuss today. So I'm going to talk about some brief background, the development of this composite long floor system, and then why we want to develop this long span kind of wood floor system. And I'm going to focus on two study. One is structural performance. We look into the level of composite action for the floor between the CLT panel and the glulam, how well they kind of act together. And we also tested and quantify the stiffness and deflection and the strength, load carrying capacity. At the end of the test, we also uh, tested how easily the whole system can be taken apart, disassembled for reconstruction. The other portion, the second half of the presentation, I will talk about the vibration performance. As many of you might be aware of, floor system, wood floor system, typically the strength, load carrying capacity is not an issue. Typically, vibration and maybe deflection, serviceability is an issue. So we have a study specifically focused on vibration performance of this long span system. We perform heel drop tests and walking tests to quantify the vibration performance. Initially, I was kind of thinking to talk about a kind of parallel study. We look into high cycle and low stress fatigue performance of the screw system and the stiffness degradation, how the screw stiffness deteriorate will affect the overall floor performance. But I cross it out. I don't think we have time today with this 1 hour webinar, right? So just quickly here, this picture here show one of the mass timber building on our campus, Clemson University. This building is called Anti-Quadabam. It's an outdoor education center and also a student activity center. So if you look at this building, we have glulam beam, right? Two glulam beam acting as a beam, and then you have the spacing between them is typically around for CLT system that with CLT panels spanning across the glulam beam. Typically, this kind of system, the span is about 20 feet or less, typically, due to certain constraint, as I mentioned, the vibration and deflection issue. And what this means here is we will need to put column quite often, quite frequently, at every 20 feet or even closer, like 15 feet here. This building, the spacing is about 16 feet. Typically, the CLT panel and the glulam beam, they are designed for non-composite. What this means here is we do not rely on the attachment between the CLT panel and the glulam beam to give us the composite stiffness. We design the CLT panel as a one-way system, as a non-composite, and then the beam as a one-way system as well, right? If you look at steel frame and other material like steel frame and concrete frame building, their typical bay area or spacing of the column, the grid size typically is around 30 feet, 35 feet, and some even up to like 40 feet here. So what this means here is wood system has a disadvantage if we limit to our span around 20 feet or less. So this means we need to put column more often. For certain programming, for certain usage, occupancy, it might create a limitation. So for warehouses and some other distribution center, so nowadays with the development of AI and data center, there's more needs to build big box warehouses. For this kind of building, typically the span is about 25 feet and even up to 40 feet here for warehouses, right? So with this limitation, I think there's a motivation for us to look into develop all wood composite system that can span up to like 40 feet here. So we started this journey long ago, back in about 2012, 2015. We received a grant from the USDA, United States Department of Agriculture, and the sub division, the U.S. Forest Service, a grant back in 2012 to develop a hollow core CLT and glulam composite floor system. The target span was like 40 feet here. And we use screw at an angle, 30-degree screw. At the end of the study, we kind of decided the screw at a 30-degree angle is a good choice. This picture here kind of show you our 40 feet span system with two glulam beam, and then CLT on top, CLT at the bottom. The width of the composite floor system is 8 feet. You can see a similar kind of precast concrete I-beam or T-beam here. This is for bridge girder. One of my colleagues at Clemson, he performed a test at the time. You can see the full scale, right? The parallel of the wood system here. So the idea here is we have the wood version as an alternative to precast concrete, either I-beam or a T section, double T section. So you can see the student here, his name is Eric Gu. He helped me, we worked together to develop this system back in 2012, and then the final test was completed in 2017. I call this version 1 of our system. So Eric Gu has since moved on. Right now, some of you might be aware of he's currently serving as a technical director for APA, taking over the role of BJ Ye for many years. He served in APA BJ. After this, there were several study by other investigator or other university look into developing like long span kind of wood floor system as well. So around 2020, Professor Barbosa and then Zimmerman at University of Oregon, Oregon State, I think, developed a rib floor system. Their target was 30 feet span here. You can see their test setup here. And later in around 2023 at UBC, Professor Frank Lam and his student also developed kind of wood floor system. Target span was like 40 feet here. Right? So there's multiple kind of solution, or I'm glad to see like multiple study out there. We have the same objective here. So there are a few ways to achieve like longer span. One other way is to use like wood concrete composite here. Very often we need a wearing surface on the floor on top. You can actually purposely design the system using actually screw or other shear stud to create composite action between the wood floor and the concrete slab on top to create a stiffer floor that can span further. However, if you look at the carbon emission for steel and concrete, like cement here, per ton of concrete actually will emit 0.78 ton of carbon or CO2 into the atmosphere. Wood is a negative carbon material. That means every time you build a wood floor or wood system, you actually store carbon in the floor system. You actually store 0.36 ton of carbon. So if you look at the global share of carbon emission, collectively building operation and construction, like building the building, account for 40% of the global CO2 emission. However, we need to be kind of more specific, like building operation, including heating and cooling. If you just look at the construction itself, the building itself, it account for about 11% of the CO2 emission. This is still huge. If we can find a way to kind of replace some of the longer span building that require a larger grid with all wood system, we can actually cut down the CO2 emission, the 11% here. So this is what we call the version 2. So in 2023, we received a grant from the ARPA-E program as part of the DOE. So this is ARPA-E stands for Advanced Research Project Agency. The E stands for energy. Some of you might heard of DARPA. It's the same kind of program, Advanced Research Project Agency for Defense, the Defense DARPA. It's for like kind of military application. So under this ARPA-E program, our objective here is to develop all wood CLT glulam composite floor system. That means we are not planning to use concrete on top. And again, the target span is 40 feet, up to 40 feet. Obviously, you can use it for shorter span, 30 feet and so on. And one of the objective here is to design the system for deconstruction at the end of the service line to reuse the cassette, the floor system, and even perhaps the glulam beam in other building here. And it is designed to be able to conceal all the MEP, mechanical, electrical, and plumbing within the composite floor system. That means it serves almost like a raised floor system. So as you can see here, we have 4 holes built into our floor system and access hole on top of the floor. And the bottom figure here show the cross-sectional view of the two composite systems side by side. If you notice, the top CLT slab is 8 feet wide or 2.4 meter wide. The bottom flange is 6 feet wide here. This means it's shorter. So there will be a gap of about 2 feet here, if you can see my pointer here. So we can actually put in a lighting system panel or acoustic panel to hide this pumping or piping system, or you can elect to not put anything there, right? And this system is designed for manufacture in a kind of plant environment. That's mean we pre-manufacture this in a kind of factory environment and ship it to the job site so that we can put together the building quickly and has a better quality control in a manufacturer kind of plant environment. So we actually have multiple design criteria and target performance. As you can see from this table here, listing from 1 to 10 here. Many of those are structural related design criteria. Some of those are environmental consideration, the carbon sequestration, and then there also the fire. Fire obviously is a consideration for us. We also consider the and reconstruction of our system here. Obviously, cost, viability, and market viability are part of the consideration if this ever become a popular, viable solution in the future. So, however, for this study, I'm going to focus on just the structural performance, right? Structural performance. And the second part, I'm going to talk about the vibration performance. There's a separate study look into the acoustic. That means the sound attenuation between the floor. This is headed by my colleague, the architecture professor, Dustin Albright. So this study, we won't cover this topic, acoustic. However, it's an important consideration. Fire, we are not talking about it today. And then the carbon storage, I'm not talking about it today, right? So let's look into the structural performance and mainly look into the composite action. How much composite action we can actually get using the sharp metal and the screw. We organize our research into three level. I like to call it like three level. Level one is the connection level. This means we look into different connection to connect between the glulam and the CLT. The connector here could be just screw by itself, or screw with glue, adhesive, or screw with sharp metal in this case. And we also tested some so-called new prototype, kind of innovative, kind of homemade connector that designed for deconstruction. I'm going to briefly talk about those later. So we perform connection tests. And then at the end, we select what are the two best candidates. And then we move on to what I call it the assembly level. We actually built two full-scale composite floor system, 40 foot long, floor system with CLT on top, CLT at the bottom, and then two glulam beam. And then we tested it for strength, stiffness, deflection, and then vibration to quantify the actual performance. And the next level is system level. This is what I call it the system level, where we put together multiple composite cassette together to form a floor. We also have a kind of short, stocky column to and to help us put together a mock-up system that look into the reconstructability of the whole system. And we also look into vibration and fatigue performance. Daily vibration it is best to study in a full system level with a realistic kind of boundary condition. Right? So this is actually ongoing. We're about to complete this study. So let's focus on just the structure and the vibration performance. So this is a reduced table from the design criteria. So for the design criteria for the span, we have kind of two levels. So at the beginning of the design, we want to achieve the preferred value. This column here, that means we want to aim for 40 foot long if possible. If for some reason, right, if we feel that we cannot reach this level, we go to our plan B, so to speak. We call it acceptable value. That means we design it for 30 feet span and then 10 feet as a corridor. Why? So this become a two-span continuous. So this system can be used, for example, in a multi-story apartment units where you have about 30 feet span for both sides of the apartment unit, and the corridor perhaps is about 8 feet or 10 feet span here. The loading is like target for 65 PSF, live load plus dead load and cell weight, additional dead load. Then deflection prefer to be L over 480 or less under service dead and live load. And then if it's for some reason we cannot achieve that, the acceptable level is L over 240. The vibration, we target maximum of 0.3% G force, G acceleration. And the acceptable level, we let it go up to about 0.5% G. This is typically quite common or recognized as an acceptable level for office and environment, multi-office use. Number 6 here, the reconstruction. So we design the level 1 is everything can be taken apart. That means the CLT panel, glulam beam can be taken apart. That means we can deassemble everything into component level, and it is still structurally sound, and you can use it in the next building. If for some reason, right, if you cannot achieve this, at least we want to achieve the construction at the assembly level. That means the glulam beam and the CLT panel, they are as a cassette. We can take the whole thing out and then move it to another building and reuse as a whole assembly without taking the CLT panel and the glulam apart here. So we started our journey with a connection test. This is the typical setup. The right-hand side show our connection test setup. We have an actuator, hydraulic actuator, 30 kip actuator can push up and down on the middle wood panel here. The middle wood panel represent our what glulam beam here, and then the two panel on the side represent our CLT panel. So and then we put either screw or screw with adhesive, screw with the rotor blast sharp metal. Kind of this drawing here show one of the tests we performed using the Simpson strong tie screw here. We also tested the rotor blast, screw, and sharp metal in this setup here. So this is what it looked like, the test. We put LVGT actually monitor the screw head pull in during the test here. So we noticed actually during the test, the screw head will actually get pulled in into the CLT panel. We also have string port to measure the slip between the CLT panel and the glulam beam. So this show a list of all the connection we tested. So we tested different screw, just simply the screw without any adhesive or sharp metal at an incline 30 degree, 45 degree, and even some of those are without incline. That means just 90 degree. We also tested sharp metal plate in between the CLT panel and glulam beam with screw using the rotor blast sharp metal plate and screw. We also make our own kind of coupler system with epoxy. So you can see the two coupler. This is designed for something easily you can take it apart, unbolt it, and take apart the CLT panel and glulam beam. We also tested adhesive with screw. What we use here is the Simpson screw, and then put the Loctite adhesives in between, try to give us better kind of initial composite action at the beginning. Usually screw take a little bit slip before it start to fully engage here. So the whole idea here is we want to achieve as high of a composite action, close to 90, close to 100% if possible at the beginning. Then we also create something called a pipe connection, basically just drill hole and then push a pipe in. These two are so-called the prototype kind of homemade connector here. So this is what it looked like for connection. Self-tapping screw. We tested different kind of screw with and without adhesive at different angle here, 30 degree, 45, and even 90 degree, mean there's no inclination. It's been just like what the drawing here showed, a screw with 90 degree angle. Some of those we put adhesive in between, some of those without adhesive. So this is Simpson, this is the Loctite glue here. I kind of mentioned the coupler system. These are kind of homemade connector. We use coupler, steel coupler, and then a bolt and epoxy into it. So the whole idea here is the thing can be taken apart easily, right? With epoxy coupler. This is a pipe system. We drill hole and then push the pipe in here. And the right hand side, the figure show the sharp metal after the connection test here with two screws as a clamping force. All right. So this kind of graph here show the summary result of all the tests we perform here. So we have different test series from 1 to 11 different consideration. I'm not going to go through every detail. The vertical axis show the force, right, of the connector. We normalize to per connector or per 12 foot, 12 inches, sorry, not 12 foot, 12 inches long segment here. The horizontal axis here show the displacement in inches bottom. The top here show the millimeter SI unit. Right hand side show the force in kilonewton, right? So let's look at a few of those. So for example, just screw right at 90 degree. So this is the highlighted test for screw at 90 degree. The typical signature for this kind of connection here is the initial stiffness is pretty low. It's not very high, as I mentioned, without any adhesive. And then it's quite ductile. You can kind of see the whole connector is quite ductile for 90-degree screw here. For the same screw, if you put it at 90-degree angle, 30-degree angle, at an inclined angle, we also test it at 45-degree. At 30-degree angle, you'll notice the initial stiffness is very high because the screw is in shear and in tension or in compression, depending on how you load it right at the beginning. So you have a very high stiffness. However, you can see the disadvantage, the drawback here is less ductile. There's not much ductility you can get, right? The displacement level is pretty low before you can lose all the load carrying capacity. The strength is pretty high, okay? Let's focus on the other test series. You can look at here using two screw for 12 inches sharp plate, sharp metal plate, the loader plus sharp metal plate. This is the test curve look like. So what you notice here is the initial stiffness is pretty high, right? The initial stiffness is pretty high. I think this is when the sharp metal start to engage grip between the two wood material, the glulam and CLT panel. And then you can see there's a drop and then the second peak here. I think from my opinion, this is what happened. The screw start to take up the load again. And then this is the final kind of behavior from the screw. And the sharp metal, I think by this level of displacement, more than 0.5 inches, I think the sharp metal plate kind of lose all its gripping, the composite behavior. If I toggle back, right, into this 90-degree screw, you can see this pretty similar. Without the stroke, the initial stiffness is pretty low. With the sharp metal, this whole curve kind of changed to have a very high initial stiffness. I think this is, in my opinion, the advantage of using the sharp metal. It gives you the initial composite action right away. This can reduce, hopefully, the vibration performance, give you a stiffer floor, right? We look into different connection. I'm just going to summarize like 4 connection. We look into actually 11 different connection. At the end, we kind of focus on these 4 to do a more in-depth study, look into the cost per square foot, using our best ability to, the current price back in 2024, the retail price for the screw, the adhesive, the sharp metal, and so on here. And we look into how easily it can be installed and then take it apart after the test. So we're trying to quantify this, how easily, and then the cost. And then we also quantify the peak strength of each of these connection here, right? You can see that kind of pretty similar, around 40 kips or so. This is slightly more than 40 kips after you put adhesive. And also the stiffness here. Stiffness is one of the big consideration. We want to get a high stiffness, and we also want to have something that we can easily deconstruct here. This is a normalization, simply kind of show how many screw we consider here. This is 1 screw, and then this is for 12 inches wide, and so on here. So at the end, we focus on using 2, as we mentioned, we selected 2, the green column, to move forward and build our full assembly level composite cassette, 40-foot long span here, using the loader plus screw and the loader plus sharp metal. And the other specimen, we use a Simpson strong tie screw and the adhesive, right? one of the rationale here is the cost. These two are the most cost effective here and kind of proven technology using screw. So this kind of figure here, drawing show the final design based on the connection level information, the stiffness, the strength, and so on, the layout of the screw and the adhesive specimen. So for the adhesive specimen, we actually just put one continuous bit of screw adhesive throughout the length. By the way, this figure, if you look at it, the right-hand side is the mid-span. I'm only showing half of the 40-foot span here, right? So this is 20 feet here. The left-hand side here, triangle kind of show the end, the support, so-called pin support of our specimen here. You can see the spacing of the screw. As it close to the support, because we have a high shear demand, we need to put like more screws and closely spaced together. Near the mid-span, the shear demand is lower, so we can relax the screw spacing a bit. And then where we have the opening, where we design to put a piping system through it, we have some reinforcement, put like more screw closely spaced together. The bottom figure here show the sharp metal plate specimen using the lotus blast sharp metal plate. Near the midspan, we only use one line of sharp metal plate here. Right? Near the support, we use actually two row of sharp metal plate, kind of side by side here. This figure kind of show the top view of the glulam beam here, right? So this picture kind of show the construction sequence. For the adhesive plus screw, we actually pre-drill all the screw, embedded it to almost the thickness of the CLT panel, and then we stop. We kind of pre-drill all the screw, pre-dry all the screw to the CLT panel, and then we put the adhesive on the glue lamp, right? Because we only have limited working time before the adhesive start to set in, so we need to kind of drill, drive all the screw into the CLT panel. And then we lift the CLT panel with the screw in place, and then sit it on top of the glue lamp beam and quickly dry all the screw into the glue lamp beam to set it within like 30 minutes. So this is what it look like. And we also need to do the same thing from below here, right? From below here. For the second specimen, design number 2, so we use sharp metal plate and screw. So you can see the graduate student, Amin, not Amin, sorry, Rolf, this is Rolf, use hammer and the template, wood template. This wood template kind of produce, we received the information from Lotus Blast, create a wood template to hammer the sharp metal plate into the glue lamp beam here. And we use the template to protect the teeth of the sharp metal plate, right? So we pre-hammer this in, and similarly, we have all the screw kind of pre-dry to certain thickness, almost the thickness of the CLT panel, and then sit it down on top and drive it in to create the clamping force here. So this picture kind of show the two specimens in our lab at the final form. The left side, you can see the access hole after we cut it. Right hand side, this show the sharp metal plus screw specimen. From the outside, you can't really tell the difference between the two, because the screw and the sharp metal plate are between the CLT and glue lamp interface. So this kind of short video or time lapse kind of showed what happened in the test near almost the tail end of the test here. We have actuator pushing down here with the loading bar spread out. So you can think of this as like 2-point load system, 2-point load system, or 2-line load system at the midspan. We have LVDT and string port at different location to measure the slip, interface slip between CLT panel and glue lamp, different location, near the midspan, near the end. We also had string port to measure the deflection at the two side of the cassette floor system to measure deflection. We also have something to measure the deflection near the support, so we can take out the bearing crushing near the support here, right? So this figure kind of show the result. The vertical axis show the actuator force. Horizontal axis show the midspan deflection. This means the deflection near here. The midspan, we have two of those. We average it out. Then this is actuator force. For two of the specimen we tested, one is adhesive with screw using the Simpson screw. The other specimen using the loader blast sharp metal plate and the loader blast screw. What we notice here is at the initial stiffness, they're pretty similar, right? You can't tell the difference between the two. Actually, our loading scheme, we load the specimen to around the service load. Then we observe what happened. We unload it. Then we load it again to the so-called LRFD design level load. Then we unload it again and observe it. And then at the end, we look at everything, document everything, and load it to destruction, load it all the way up. And then we kind of, what you see like this kind of zigzag, that means some of the screws start to pull out and fail. And the shear cracks start to form in the glulam panel. So what we notice here, as I mentioned, the initial stiffness, both specimens are pretty similar, almost identical, right, for all practical reasons. However, you can kind of argue the sharp metal is more ductile. At least this specimen kind of show more ductile. It kind of, we push it further. We can able to push it further without seeing structurally compromised. The adhesive one is more brittle, if you will. However, the peak load, the peak strength is about the same, almost the same. And we see kind of crack, shear crack near the access hole here. I'm going to show more detail here. If you look at this video here, yeah, pay attention to here. I'm going to start it again. You're going to start to see crack form here, horizontal crack, right? This is the one of the big initial kind of failure, the sudden drop, kind of the shear crack here. We have screw.
Because the opening.
If you ask me to redesign it again, perhaps
that opening crack.
we should put more screw here to kind of help reinforce the shear crack. So this is what happened here. This picture shows the screw for the sharp metal. We have screw here. You can see the shear crack. And then actually shear crack all the way meet up with the finger joint of the glulam lamina here and all the way here. If we get to redesign it again, I will recommend we put more reinforcement around the opening whenever you have opening for the traverse opening to limit this shear crack. Very similar for the other adhesive specimen using Simpson screw, we also see similar kind of crack form near the access hole opening, right? So this show the summary test result for the structural adhesive using screw and adhesive, and then sharp metal plate, both we have screw in it. This is the back calculated force, what we think the force inside the connection here, the tested load, and the nominal design, the hand calculation, the engineering design. So the peak load versus the nominal calculation, the ratio is about 3. For the shear, mainly the shear kind of carried by the glulam beam here. And then with the access hole, you actually have reduced shear capacity limited by this hole here. The nominal design value, what we think the design value is, and then the tested shear capacity. The ratio is about 1.1. As you can see, moment, we have way higher moment capacity than the design value. For deflection, we target L over 480. Actually, the deflection, this floor system is quite stiff here. The deflection at the service level is not an issue. By the way, service level, well, let me come back here. That's been the deflection at this level, the service level. So we target it to L over 480. In fact, we get something very low here. Actually, it's L over more than 1,000. There's no issue. So the conclusion here is strength is not an issue. Even deflection is not an issue, right? So let's look at what kind of composite level we can achieve here. We can easily calculate what is the full composite EI by calculating, by assuming the stiffness of the connector side perfectly stiff. You can calculate EI infinity, and then EI no composite, that means without any screw. These two are easily computed. And then EI effective, we actually achieve this using back calculation from our test. Look at the bending stiffness and everything, back calculate the EI. Or you can use something called the mechanically joint beam theory. The European code had this information. You vary the alpha connection stiffness from very low to very high. So this is what happened here, the test result, okay? We can compute the EI non-composite using theory, and then the EI full composite knowing the stiffness. By the way, we actually tested the stiffness of individual glulam and CLT panel. And then based on our test, right? Before we get to the test, we can actually use a mechanically jointed beam theory, vary the stiffness of our connector to come up with this curve here, right? The composite curve here. Horizontal axis show the stiffness of the connector per spacing, right? Kilo Newton per millimeter, and then per millimeter of distance here, length. From the test, sharp metal kind of achieve about 93% based on here, right? About 93%. This is 0%, this is 100%, 93% of composite level. The adhesive bar screw kind of a bit higher, but they're almost the same, 95%. So based on our test here, we can kind of conclude both of them almost achieve very high composite level. So at the end, we also look into the construction here. So after the test, we look into how easily we can reverse the screw and then take it apart. You can see all the screw kind of bend, right? Yielded and all. We can quite easily take it apart, even the sharp metal and the adhesive one. We have a kind of video kind of show what it look like. Right. We can kind of easily take it apart here. So the kind of key takeaway here is the structural performance. We achieve the long span load carrying capacity, no problem. Load carrying capacity for deconstruction, deconstructability as well, we achieve those. Both specimen, adhesive and sharp metal plate, achieve similar stiffness in the elastic zone service level. They have comparable peak strength, almost identical. And then both of them achieve very high composite action, like 90% degree of composite action. So the next step, actually, we are kind of working on numerical modeling. And also, as I mentioned, we are entering phase 3. We actually built 2 of the cassette side by side and put it together and look into different connection between them, half lap, surface spline with a plywood panel, and also like butt joint, right? Using just glue and an angle here. So next, let's quickly look into the vibration performance, right? Vibration. So what kind of factor affecting flow vibration? As the span length, if you increase the span length, typically the vibration will be more if you increase the span length. If you reduce the mass of the system compared to, let's say, reinforced concrete or concrete, wood is a lighter material. If the mass reduce, usually the vibration will increase. Stiffness here, usually wood, right, is like less stiff compared to concrete or even steel here. This means if stiffness reduce, the vibration will increase here. Like damping, obviously, if the damping is reduced, the vibration will reduce here. The inherent damping of this floor system is pretty low. I'm going to show you later on. So what this means here is maybe it's very likely this kind of long span floor system are susceptible to vibration or service related issue. So in this study, part of the study, we focus on quantifying the vibration performance of these two system here using adhesive and the other using sharp metal plate, and then both with screw. Then we also evaluated the influence of opening. We have different access hole, cut opening, and look into how much effect it has on vibration here. So again, quickly, these are the two systems we study. So just quickly for vibration, acceptable level for vibration is pretty subjective. We have different acceptable vibration curve here. So for example, office and residential, the red color curve here are the so-called acceptable vibration level. It is a function of the natural frequency of the system here. The horizontal axis show the natural frequency, the vertical axis show the peak acceleration of the floor, right? So we need two kind of different tests to achieve these two information here. One is to perform the heel drop test or the modal testing to obtain the mode shape, damping ratio, and natural frequency. So when we get the natural frequency, we know where we are for the flow system in the horizontal axis. The vertical axis, then we need to walk around using certain, representatives, human weight and the walking speed, and then record the vibration level, and then we know the Y information. So if, let's say, the two data meet here, this means you're okay. Below the acceptable curve here, this means you're okay. The vibration level is low. If for some reason, right, it's above this level, this means, well, this is not recommended. It's not a good idea to use for office or residential units. Likely you're going to the occupant going to feel like a lot of vibration here. Right? So we conducted like heel drop tests for our full span system. You can see Amin, our graduate student here, lift his heel and then drop down on this something called the force plate. And then we record the force displacement, his time history. We also have accelerometer throughout the floor system to record the vibration at different locations. Then we put these two information together to come up with the vibration performance. So this show the heel drop test setup. We have the heel drop force plate at this location. Notice that this is the mid-span, right? We are not putting the force plate at the mid-span. I'm going to explain why. Typically for the heel drop test, you need to put the force plate at the off-center location, not at the mid-span. Somewhere here is a good location here. Then all these nodes show the where the accelerometer are located. So we put accelerometer here, jump up and down, and the force plate record the behavior. And then we keep doing this for over and over again for different locations throughout the floor. And then we collect all this information. We are using fast Fourier transform. We're able to extract the first mode frequency is about 9 Hertz. Pretty similar for the sharp methods at 8.8 Hertz. But for practical reasons, about 9 Hertz. All right. Second mode is about 18 Hertz. Third mode is about 24 Hertz. And then you have more. But I think the first three natural frequency are enough here. So as you can see, first mode, second, third mode, and then we also look into without hole. Then we start to drill 2 hole, we perform the test again. The natural frequency really didn't change that much, right? Then we drill 4 hole. You can see a 4 hole, and then we perform the vibration test again. The natural frequency didn't change that much. By the way, you kind of lose a little bit stiffness, and also you lose a bit mass. So there are multiple things going on here. Then we also, at the end, we drill hole on top here, cut 4 access. So at the end, the summary here is all these minor hole cutting have very little influence on the vibration behavior, the natural frequency. So this is the first mode. Using the heel drop test, we can get a first mode response. Okay. And then this is second mode. Basically, it's a torsion, twisting mode. So for one single floor system, by the way, this is not realistic in my opinion. For the full floor system, once you have things side by side connect together, the twisting mode will be disappear. Then the second mode won't show up in the full floor system. Then you have third mode, the double curvature. That is why you do not want to put your force plate at the midspan. If you put it at the midspan, you're going to miss the second mode, right? Because here there's no movement here, right? So that's one of the reasons why we want to put our force plate off the center. We also look into the natural, the damping ratio using the half power bandwidth. The summary here is the damping ratio is pretty low for this system because we get full composite. There's not much movement between them. So basically it's like 1 to 2%, right? So almost very low. Next year, we perform walking tests. That means, we just walk around here from here to here and then walk around the floor system. This is a walking path and with 2 different speed, 1.6, about 1.6 step per second, right? 2.2 step per second. You can think of this as quite fast walking, slow walking. Then we measure the acceleration at different locations. This is what it looks like, right? And then using the root mean square. We don't use a peak vibration, just a root mean square. Kind of average this red color line and pick out the high value to quantify the vibration. So this is what the result look like, right? 2 tests. If you walk slow, the vibration level, remember the natural frequency is about 9 Hertz. If you walk fast, you get more vibration. This is the worst case, the worst location. By the way, if you look at all the data, it looks something like this, right? A distribution. We have many locations. If I come back here, we have many locations, right? Many locations. The worst location near the midspan give us this point here. However, this is for one single floor system, right? One single floor system. As I mentioned, right now we are entering like last phase of our research. If you put together the full system level with multiple cassettes put together, likely the natural frequency will increase, shift to the right, and then due to them connect side by side, you can mobilize much more the mass and of the adjacent cassette system. Likely the vibration will reduce. So this is what we are still studying. This is my speculation, right? So this is still, jury is still out here. So to summarize here, Our natural frequency for our floor system about 9 Hz. Very similar for both again. Very low damping for this kind of floor system. Once you achieve full composite level, the damping ratio is very low. In this case, about 1 to 2%. That's about it, the inherent damping. By cutting some excess hole at the strategic location, it has very minimal influence on the natural frequency, less than 3%. For single isolated composite cassette, right now, we don't quite meet the requirement. However, we kind of speculate if you go to system level. Right now, we are still working on it. Likely the vibration issue will be taken care of. So, and this is what we kind of working on, testing the whole system level, different connection level side by side. This is actually what it looks like right now in our lab. We have two kind of short column, 4 short column with a giant girder, and then to hang the composite cassette here to the giant girder here. And then we're actually using the Alumega of Lotus Blast for the girder hanger here, right? I think that's all I have. Thank you for your attention. We still have about maybe 9 minutes. Open up for any question if you have. Thank you all.
Thank you again, yeah, for that presentation. I have the Q&A here open. I don't see any questions in the present moment. But if they do come through here before we get off, I'll be sure to pull them up. I do want to mention to everybody again too, as I do in all of our webinars, if you do have any questions that come up after this webinar is closed in a day, a week, or a month, please feel free to reach out. You can reach out directly to it's mkt.na@rothablast.com. And for a webinar like this, I'll be sure to connect you with Professor Pang specifically on those questions. So one question came through. Personal experience of removing PL premium is very different from what is depicted. It's practically welded once cured. If you assessed deconstructability after destructive testing, had the adhesive already failed in shear and was therefore easier to remove? In practice, could disassembly without destructive testing be more challenging?
Yeah, this is a very good point here. You kind of pointed out the issue here because due to the limitation, right? We do not want to build the full system and then just to take it apart, because it takes quite a bit of effort and resources for us to build the full system. Yes, if the system are put together and it is just subject to service level loading without seeing the way overload destructive loading, likely taking apart the CLT panel and glulam would be maybe challenging because the bonding right between the adhesive is kind of in full bonding. That is why we also have a second design using the Lotus Blast. The Lotus Blast system, we tested it at the connection level. We can easily take it apart after we put it together. We can separate them. Yep, you're right here. In my opinion, yes, if you can retain the option of taking apart the CLT panel and glulam, it's good. However, I foresee this system to be used as a full cassette. You just leave the full cassette and then move it to another new structure or building to reuse the full cassette. So in that case, there's no need to take apart the CLT panel and the glulam. But it's a good point. Our test is destructive test, so the glue bond has already been kind of damaged, and that's why it was much easier to deconstruct. However, with that mentioned, right, the other hand, the screw actually much more difficult to take it apart because some of them are already bent into double shear and so on. Yeah. That was a good observation. Thank you.
I've got another question that asks, when you reloaded the cassette specimen, it looks like there may have been some residual deflections. Green load displacement curve. Did this impact the behavior?
Actually very little. Yeah, let me go back to the graph. Yeah, good observation here. Very little. So, yep, you kind of see, yep, when we reloading it, unloading it, it's not exactly following the initial path here. part of it is kind of due to the crushing a little bit at the support, little bit, right? So it settled down a little bit at the support here. And then when we reloading it, it almost followed the initial path again for some reason here. You're right, they are not completely linear elastic. There's a little bit loops here. However, this is pretty minor. We don't see this like big loop dropping here. There's not much residual displacement, but this is a good observation. We load it up and then unload it. We didn't do the vibration test, to be honest. We performed the vibration test before we performed this so-called destructive test. So all the vibration tests were performed prior to this so-called destructive test.
Cool. Another question, have you any thoughts of how the CLT panel orientation affects behavior?
Okay, for the CLT orientation, right now, this is designed for the strength axis is parallel to the glulam direction, right? Unlike other conventional CLT building or mass timber building, you have the CLT panel running in this direction across the glulam beam. To achieve like long span composite kind of like cassette, we actually prefer to have the CLT panel running in the long direction. So you have the outer layer, right? The top and bottom layer. This is a 3-ply CLT. Is in parallel to the strength direction here. So the idea here is to create something similar to the precast concrete double T or single T system here. Yes, you are right. If I put CLT panel across, especially if you have gap here, I think the overall composite action or the overall stiffness of the system will reduce significantly. In particular, the bottom flange, right? The top flange are in compression, bottom flange, there'll be in tension. Yep, good point.
I've got another question here that asks, what part of the code allows using glue, or is it this pure experimental?
We rely on the glue for just serviceability. We're trying to achieve the stiffness, right? We are not relying on the glue for strength here. In fact, if you, this kind of graph kind of show the peak strength for both are pretty similar, and then the initial stiffness. If you go back to the here, right? The screw will be our final strength load carrying element. The screw and sharp metal is kind of helping us at the initial stiffness. If I go back to the screw at 90 degree, the initial stiffness is pretty low. So the adhesive is kind of helping us to create this bump here. And then the sharp metal, same thing. So I would say I don't think we violate any code, right? There's no rule, in my opinion, prevent us from using glue. In fact, light frame, it is a good practice to put glue to get rid of the annoying kind of squeaking noise. Yeah. Hopefully this answers your question.
And then the last question that I see in the chat at this moment is, in terms of manufacturing ease, what seems to be easier to assemble for future fabrication partners? Time, ease of install, etc.
So far, we kind of have a pilot scale construction put together. I think based on our limited experience, we only put together one specimen each. I would say both have their challenges. Sharp metal, where is it here? Sorry. Let me go to here. Yeah, the adhesive has its challenge here. For us, the set time is pretty short. We need to have very quick action to drive all the screw in. I can see in a planned environment, if you are designed to just making this kind of cassette, you're not going to use the screw, the drill to drill individually. You perhaps come up with certain mechanism to drive multiple screw at once. That can ease up the construction here. And then here we are kind of hammering things one by one. So it's pretty slow. I see in a plant environment, you have a template, right? Very long template, just press down, even using certain hydraulic actuator. I would say sharp metal can be easily put together in a plant environment with the right setup. And then adhesives due to the set time. If you get the process going, I think both are doable, right? In my opinion.
Awesome. Thank you. Yeah. So that's all the questions that I see in there, and I see we're right here on 12 o'clock.
Okay.
So I just want to thank you again for presenting with us. And I'm surprised though in that whole testing room there, I don't see any tiger paws.
Oh yeah, we forgot to put that. Usually we like to put some of those.
Yeah.
All right.
And then just for everybody that's still on, thank you again for joining us today, and we hope to see you in the future for upcoming webinars. Like I said, we got 2 more to close the year, and we look forward to those. So enjoy the rest of your days.
All right. Thank you all. Feel free to reach out if you have further questions, right? Email me. Thank you. Bye-bye.